really a privilege to be able to speak in front of so many experts, and also my friend, Dr. Phadke. I always call him that way, never use Arun, and we get used to it. And also Kasung is here, and then my department head, Dr. Thorp. What got me interested in the phaser is actually not the practical reasons, but more, not about the lights on or lights out, but more about the fascinations that eventually Dr. Thorp explained the propagation, the electrical, mechanical propagation that's happening in the power grid. And I just dying to find a way to see it. And I see pieces of it, but I never get to see the whole picture. And that's how I got motivated to come up with something that may be cheap, that we can actually measure ourselves as a university. And remember, I spent most of my career at Virginia Tech, as being the phaser project goes on, and I learned slow, but it got into my blood regardless. So what I started to do is to come up with a simple, cheap thing that can actually do measurement. That the only thing that seemed feasible at that time to do is to measure frequency. So the frequency always stay the same regardless if you measure it at the substation level or if you measure at the house level. So that's how we start looking into possibilities of building something cheap, and then a university could own, and the student can have the data. At that time, the data is also a big issue. Still now, that you wouldn't get data, complete data for the entire interconnection. You get a piece from TVA, get another piece from someone else, but you couldn't piece them together easily, and you still have problem doing that now even. So we started looking for ways to do this, and when of course I first approached Dr. Phadke, I said, what do I do to do a very accurate frequency measurement? And he happened to have developed a single-phase PMU algorithm, and that calculates single-phase phasers. Remember, three-phase is a spatial vector that's rotating in space, and it's reasonably easier to do the phaser in three-phase, but it's actually a little twisted for the single-phase. So he already developed the single-phase algorithm for calculating voltage, phase, or current, doesn't matter, phasers. And all I needed to do is to basically use it. And he also had developed a robust technology to calculate the frequency out of those single-phase phasers. Those were made for under-frequency relay application. So one of my colleagues, Rich Connors, I wasn't really going crazy about building them because I'm not a hardware person, but he was. He just feel, oh, this would be fun. Let's do it. Let's do it. They keep pounding on me on that. I said, I have no knowledge about this, but eventually we were able to enlist the help from Yilu Liu because he built the first PMU, and by hands, and he was able to sit into discussions on what we can do. So eventually we were able to put together a single-phase baby PMU, which takes the voltage phasers only, and able to produce a good frequency. And my original thinking was, if I have enough of this, I would be able to see the waves that Jim Thorp and was trying to advertise. That was very, very fascinating. So I usually approach things because it's less practical in the sense I wanted the lights on. I really wanted to see how it propagates, and that's how we started with the small unit project. Of course, there's other aspect. There are people who ask, if I get the frequency, can I see? What can I see? Is there anything I can see from the frequency measurement alone? And that become part of the motivator. Okay. Okay. So this is the first unit was built out of a Cisco router box we bought from surplus, and then we put the algorithm that Dr. Phadke developed originally, and this became the first unit that was started in 2001, and we got the first one running I think it's in about 2002, but never really hardened enough. So 2004 is when we started to send those out. And here is the latest version, and we have gone through 3 or 4 generations of it. Yeah. This is one of the students who developed the project, and then the student happened to be legally blind. And we were actually stuck for several months because of the accuracy problem, but we realized he actually unplugged the 8-bit reverse in a reverse way. He couldn't see as well. This is where they are now deployed. It's about over 200 some in North America. We also have some in the major, trying to cover the major grids in around the world. So this is the coverage, and some time earlier, and we had more in other part now, and we got one in Chile. I really like to put some in Russia, but I have never been successful. So I was hoping someone will get there and then and be able to put some of those in. We actually put quite a few, sent several to India before the blackout. But the response we got is the electricity is owned by the government, and the citizens are not supposed to get signal out of it. So we haven't been able to deploy it. Okay, so what do we do with it? Besides, looking at the waves, we do look at the waves, and quite a few of you have seen the wave propagation videos. And we do a number of things, and some odd things, and really not the mainstream application, and all kinds of odds and ends. One of them is locating an event. Whenever event happens, the frequency start to change, and this delay of arrival give us information on where the event originates. So, and that get triangulated and sent out automatically. And some of you is holding an iPhone that gets messages, a few messages every day. We also do oscillation reporting automatically, and we also do use those information for looking at the ambient, because ambient give you the update on the oscillation mode continuously. And you can switch between units and look at the ambient that give you a lot of information on oscillation mode and damping. This is one of the typical oscillations we see in the eastern interconnection, and usually you get a 3-way oscillation, sometimes 2-way, and basically developing ways to estimate location mode and dominant frequency. And this happened to, I cannot give any presentation without showing at least one movie. This is basically showing, okay, if I instrument at such a device at each wind generator, I can tune the wind generator algorithm so that whenever you have an oscillation, and the wind can actually be a very effective way actuator to damp out the oscillation. Okay, you can see that at the top shows the wind was damping out the oscillation, and the bottom one is the original signal. Okay, so now we justified that we probably need one in each wind farm or wind generation side, and so it's probably solar case. You can look at the frequency, and you can see the deviation whenever there's an islanding. This is captured for the eastern and the WCC on the bottom and eastern when the system islanded. And remember, when we have a lot more sources, and that means the DG side and the wind farms and the solar farms, and you will deal with more islanding cases. Okay, and then the next interesting thing we can look at along this line of islanding is monitoring hospitals. So whenever hospital is on off-grid, you can easily see that from this diagram looking at the frequency. Okay. Another odd application is forensic analysis. And the 60 Hz hum is embedded in all the signals, into even the lighting, into the vibration, into many other things. And the audio is one of them. You can use the signal from the system as a signature to identify the time, location of any recording that takes place. And this is one of the true event comparison. And feedback is one of the things that you can easily discover with the distribution level measurement rather than having the high and side measurement. Okay. You can measure it without plugging in. So if you develop antennas that takes the electromagnetic field, you can develop phasor measurement unit that doesn't require a plug-in. You can just do a survey and measure the magnetic field, the electric field, and come up with a PMU unit without touching any things that being measured. We are lately getting into the alternative ways for timing. This is the Yilu, and we were able to fit that into our system in place of a GPS. So this could be providing an alternate a solution for instead of GPS system. Okay. Okay, this will give you a rough idea of the accuracy for the Yilu system. It's sort of within 100 nanoseconds. So remember, we only need about 1 microsecond for good angle accuracy. For frequency, you need much less accuracy. We were able to come up with very accurate measurement, as good as the GPS could provide if we use Yilu as a timing. I understand this might be a good alternative as a backup. Okay. Finally, I'd like to thank them both again for coming up with the technology with the phasor, and without that, I don't think the center that the Phil helped funded and the NSF Engineering Center would be a possibility. I'm sure there will be a totally different name for a center, or may not be even a center in the power system area. So that, and we have many years to work on, and I hope they will stay active to be our scientific advisor board and as the active speakers for the center. And with that, I want to thank both of them. And I think I'm not going to win the computation of how early I know either one of them. I do remember the day I first met them, but I feel I'm the privileged one who has the longest, the daily possibility of interacting with them when I was a faculty at Virginia Tech, and being able to continue that as long as they're around. And I'm hoping they will be around for a long time. Yeah. Okay, thank you.